Hey, welcome back to Abstract Algebra. In this lecture, we're going to, well, achieve our main goal. I've got it written here. What I'd like to show you guys is a recipe for how, if somebody gives you a field and they give you some polynomial over that field, a non-constant polynomial over that field. In particular, we said last time that we're going to assume it's an irreducible polynomial over that field. I'd like to construct an extension field of your given field that contains a zero for your polynomial. Yeah? So in some sense, I'd like to solve the old math problem of finding zeros for polynomials by just inventing the place where those zeros exist. So let's just get right into it. We have kind of done all the legwork. You guys have worked hard this course, especially in the back half of this course, working online, trying to learn about rings and fields. And so now you get to just enjoy the fruit of all of your labor. So let's start by kind of making a checklist here of what we know. So you hand me some irreducible polynomial over a field, yeah, then we know that the ideal it generates is a maximal ideal. I tried to give you some references here. You could pause and look as we go, or you can look all this stuff later, but that's theorem 4, 5, 11, that an irreducible polynomial generates a maximal ideal in the polynomial ring. Okay, going back a little bit further in our work, if you have a maximal ideal in a commutative ring with unity, the quotient by it is a field. So the polynomial ring f of x divided by this ideal generated by our irreducible little f is a field. That's theorem 442. You can pause and go soak that up. Now I'm going way back into this third section of chapter 4, the canonical homomorphism. The author denotes it, I think, by phi. I like eta, that just sends a polynomial to its coset, right? The canonical homomorphism just takes an element of the numerator and sends it to the coset. That's a ring homomorphism, and its kernel is precisely the ideal generated by f. Okay, that you can see it's theorem 432. Okay, so let's prove a little lemma here, that the restriction of that canonical homomorphism, the canonical homomorphism's domain is all polynomials. But if I restrict it to just the constant polynomials, f, then it's one-to-one. It's onto its image. Every function is onto its image, and it's a ring homomorphism. So that means its image is going to be isomorphic to some subfield of E. Okay, so E is going to end up being our extension field of F, but we don't really theoretically have it containing a copy of F. It contains a copy of something that's isomorphic to F. That's what our lemma says. Okay, well, so we know it's a ring homomorphism. We know it's onto its image. I got to show you it's one-to-one. A ring homomorphism is one-to-one if and only if the only thing it sends to zero is zero. So that's how I'm going to start this proof, is I'm going to take some constant polynomial. Why? Because I'm restricting eta. I'm only thinking about plugging in constants. So I take this constant polynomial and I plug it into eta, and by definition, that's the coset containing the polynomial a, the constant a. And that's in the kernel, right? A is in the kernel of eta. I could write that as another step. A is in the kernel of eta if and only if eta of it is zero. Zero is the ideal itself. Remember, in a quotient ring, it's the coset containing the additive identity. But a coset containing A is equal to the ideal itself if and only if A is in that ideal, right? This is the ideal generated by F. So that would mean our constant polynomial F, A, is a polynomial multiple of F. There'd be some G that we can multiply F by, but F is an irreducible polynomial. It's not written in this lemma, but it is throughout this entire lecture. F is an irreducible polynomial, so its degree is at least 1. So wait a minute, how am I taking something of degree at least 1? I'm multiplying it by some other polynomial and getting a constant. The only way this could possibly be true is if G and A are 0. Yeah, if G is a non-zero polynomial, the degree of F times G is at least the degree of F, which is greater than or equal to 1. But the degree of this side is 0. Okay, so the only way we're getting out of this is if G and A are 0. So eta is one-to-one. If it's a one-to-one map, it's onto its image, it's a ring homomorphism. That proves the lemma. F is isomorphic to eta of F, which is a subfield of E. Okay, now something for you set theory purists is probably going to be a little bit uncomfortable, but oops, sorry, this thing I see is lagging behind me a little bit, but it's caught up now. Um, so I'm going to do something. This F, F is isomorphic to its image under eta, but they're not equal. F is a set of field elements that I'm thinking of as constant polynomials. Eta of F is a set of cosets. So they're not equal in the category of sets. But they are isomorphic. So we're going to go ahead and just identify. So for every field element A, I'm going to feel free to just interchange A and the coset that contains A. So I'm just going to think of A as its coset when I'm trying to think of E as an extension field of F. So this is not, rigorous set theory, but the hassle of inventing a bijection and using all of that notation, it's not really worth it. What the lemma says is that the cosets that contain all the constant polynomials is just like the field of constant polynomials. So we'll just kind of ease notation sometimes and write this instead of that. Okay, cool. So now we can accomplish our goal. I'm going to take a specific coset. I'm going to let alpha be the coset that contains x. X is a polynomial over f of x, so it has a coset. For notational ease, let's write I instead of this f of x with all those parentheses. It's driving me crazy. So alpha is just the coset containing x plus I. Okay. And now let's take our irreducible f, and I haven't done it in this lecture yet, so let's name its coefficients. I'm calling them a's. So these a's, the a sub i's, they all come from f, right? And I might choose, if I want to think of them as the coset containing a sub I, because we're identifying f with its image under eta, the subfield of E. E is a bunch of cosets. So if I'm talking about elements of E, I should be writing cosets. But sometimes I want to relax and just write the set, like the element AI. Okay? So if I do that, if I take our polynomial f has coefficients. I already said it, a0, a1, a2, those things are all in little f. Well, down here, I'm writing them like they're in E. So a0, I'm going to write a0 plus I. A1, I'm going to write it as A1 plus I. I wish I would have highlighted these as I was going. Maybe I'll switch colors and do one. What's up? A2 up here, I'm going to write it as A2 plus I. You guys with me? AN plus I. So that's just kind of formally how I think of F as a polynomial over E. It's a polynomial in the same indeterminate X. All right. Now I'm going to evaluate it at this alpha. I'm going to evaluate f at this alpha. So what does that mean? I need to replace the indeterminate with alpha. Alpha is the coset x plus I. So here we go. Should I color it as we go? I have to plug in alpha for x to the 1 right there. I have to plug in alpha for x squared right there. I have to plug in alpha for x to the n in the last term. And now I'm going to just do a bunch of coset manipulation. Let me scroll this once and then let it stop so it's not lagging. So not a lot going on here at the beginning, just copying some stuff. X plus I is x plus I. But in this one, I have to take x plus I squared. Well, by the way you multiply cosets, you get the coset containing x squared plus I. Likewise, the coset containing x plus I cubed is the coset containing x cubed. The x plus I to the n, it's the coset containing x to the n. Okay, the next line, more coset multiplication. Nothing happening with this constant term, but the product of these two cosets, a1 and x, the coset containing a1 and x, that's the coset containing a1 times x. The coset containing a2 times the coset containing x squared is the coset containing a2x squared, and so on. All right, the coset containing an times x to the n is just the product of those two cosets. And then finally, in the last line, I'm adding the cosets. I have the coset containing a0, a1x, a2x squared, and so on, all the way up to anx to the n. When you add cosets, you add their representatives. So I just add all those things together. I get the coset containing, that's just f of x. That's just f of x. And maybe I should remind you that I is the ideal generated by f of x. So that coset is the identity coset. So that's 0 in E. That's the identity, the additive identity in our field E. So what have we done at the end of the day? When we evaluated f at alpha, we got the additive identity. That means that alpha is a 0 by definition. Cool. Cool. Kind of seems like smoke and mirrors, right? I mean, I wanted to find a 0 for this polynomial. So what I ended up doing was constructing this extension field that's a set of cosets. Then I showed you that the constant polynomials are all distinct cosets in it, so they're isomorphic to f. And then I just kind of made the coset containing x be the 0 for f. It seems like a little bit of an artificial construction. If you're not disturbed by it, I'm kind of puzzled, because it is a little bit disturbing the first time you see something like this. You can watch the video again and see if you feel less disturbed after the second time. Let's look at an example. I think I owe you an example after sitting through that. Let's take our polynomial x squared minus 2 over q. It's irreducible over q by the degree 2 or 3 theorem. Yeah, the square root of 2 is not rational. So that's an irreducible polynomial. So this E, the quotient of the rational polynomials by the ideal generated by x squared minus 2, is a field. And the coset containing x is an element of that field, and it's the 0 for f. So somehow it's supposed to be the square root of 2. Or I guess maybe the minus the square root of 2. But how is that? What does this mean? We know what the zeros for this polynomial are in the real field. They're plus and minus the square root of 2. So what is this thing, and what is E? Where are the real numbers? Where's the square root of 2? Is E the real numbers? Well, we can answer all that question with our favorite tool, the first homomorphism theorem. We're going to use the first homomorphism theorem. First of all, as a little preliminary, if you take an arbitrary polynomial in Q, divided by x squared minus 2, the remainder you get is at most linear. It's either the 0 polynomial or its degree is less than 2. So it's a linear polynomial. So I've just kind of written that in the fly here, that it looks like ax plus b for some a and b and q. Maybe they're both 0. Maybe the remainder is 0. Maybe a is 0 and b isn't. Maybe it's a constant polynomial. But any polynomial of degree less than or equal to 1 over q has to have that form. All right? So g minus that remainder is a multiple of x squared minus 2. So g and that remainder represent the same cosets. Can you guys see there's a lot of parentheses going on here? This is the ideal. So I'm looking at the coset containing g and the coset containing ax plus b, and they have to be the same. So if I summarize that, every coset in E can be represented by a linear polynomial. Can be represented by a linear polynomial. You don't have to use an arbitrary polynomial when you're taking a coset. It can be a polynomial, I shouldn't say linear, of degree less than or equal to 1, more precisely. Pardon me, degree less than or equal to 1. Here's another little exercise for you. These exercises get me off the hook and keep the video short, but the evaluation homomorphism square root of 2 from the rational polynomials into the real numbers, its kernel is precisely the ideal generated by x squared minus 2. This is a fantastic exercise. Do it with a pick-a-point proof. You'll use the division algorithm. Okay, if something is in this kernel, it's a multiple of that. Trivially, any multiple of this is in the kernel, but you should write it down. Okay, so that's a ring homomorphism. It's not onto. I'm going to write that down to emphasize it. It's not onto R. Not every real number is achievable by evaluating a rational polynomial at the square root of 2. It's not an onto ring homomorphism, but its kernel is the ideal generated by x squared minus 2, according to your exercise. So if we use the fundamental homomorphism theorem, the first homomorphism theorem, pardon me, it says that this quotient field, E, q of x mod that ideal, is isomorphic to the image of phi of root 2. Yeah, it's not isomorphic to R because phi of root sub root 2 is not onto, but it's isomorphic to its image. Well, what's in that image? The image, well, since every coset down here can be represented by a polynomial of degree at least 1, when you evaluate those things at the square root of 2, you get expressions like this. You get a root 2 plus b. A and b are any two real numbers. Okay? So that thing, which is quite literally a subset of the real numbers, is a subfield, and it's a subfield isomorphic to E by the first homomorphism theorem. So we can write E, well, equal I want to, but actually there's a common notation for it. Let me write it. Oh, I wrote it below, sorry. This E is isomorphic to this set, A times root 2 plus B, where A and B are any real numbers. It's a subfield of the real numbers, and that subfield is typically written like this. You pronounce it on the telephone, Q adjoin root 2. What we've done is we've enlarged the rational field. We've enlarged the rational field. You can definitely see that Q is a subset of this set Q adjoin root 2 because you can take A to be 0. Let B be any rational number, right? So it's a field that contains Q, but it's bigger than Q. The square root of 2 is in there, right? The square root of 2 is in there because, can you choose the A and B for me? You take A to be 1 and B to be 0. So it contains Q, but it's bigger than it. It's a proper extension of Q. But it's also a proper subfield of R. Not every real number looks like that. I'm not going to prove this to you right now, but you could probably imagine that things like you can't realize the number pi as an expression like A times the square root of 2 plus B, or even the square root of 3. If you wanted, we probably could give a proof of that. So we have this extension field of Q, and it contains a square root of 2. It contains a 0 for our irreducible polynomial, but it didn't end up being all of the real numbers. All right, so if you take the second semester abstract algebra course from Dr. Getz this fall, well, I mean, the topics are in some sense up to him, but it's a traditional topic to kind of continue this discussion, to kind of ask questions like, well, are there other fields between the rationals and the real numbers? There certainly are. What can we say about them? How do they behave? This business, this field that we happen to construct contains all the zeros for our polynomial f is x squared minus 2, because there's just two of them, plus and minus 2. So other questions that you'll kind of possibly talk about with Dr. Getz are things like, you know, given a polynomial and we construct an extension that contains one of its zeros, does it always contain all the zeros of that polynomial? The answer to that one is no. How can we find a field that contains all the zeros of a given polynomial? What can we say about that field? How do they behave? So all of this stuff is kind of usually called under the heading mathematics field theory or field extensions. And if you look in the table of contents of our Herstein book, we're not going to cover it in this course, but he kind of speaks about this stuff in chapter 6 a lot in the special topics. He talks about some field theory. Okay, so just to summarize, I'm going to end this lecture stating it with the person's name properly written next to it. What we proved in this lecture is something people call Kronecker's theorem. The Kronecker's theorem, you can see it stated there, but it says if you're given a field, capital F, and a polynomial over it that's not constant, can't be a constant polynomial, then you can construct this extension field E, and you can construct an element, or not construct, but there's an element in this extension field E called alpha that will be a 0 for your polynomial. All right, thanks for listening.